some calculations. Based on data he knew that the moon would go once around the Earth in 1 month, and he knew about the distance of the moon to the Earth. He didn't have the law how to calculate this, but he had an idea, and then he did some calculations, and it just didn't fit. Later, when he was a member of the Royal Society, there were some people speculating about this also, and the speculation was that the law of gravity was a law in which the force between two masses would diminish with the inverse of the square of the distance. And then Halley was one of the persons. Halley, you know, from Halley's comment. Halley asked Newton, suppose one body is attracted by another body with a law in which the force diminishes with the inverse of the square of the distance. What would be the orbit of that body, or one body around the other body? And Newton said, an ellipse, of course. And then Halley said, why, of course? How do you know? But Newton said, well, I calculated it. And then Halley got excited and said, well, can you send me the calculations? And Newton said, yes, and it took him 3 years or so to send him the calculations. Because then he sat down to write this book, which I think is the greatest scientific book ever written. It's called The Principia. He invented calculus, by the way, for this, because he needed it to do the calculations, so he invented calculus. And he came out with a figure which was right on the nose. He now had better data, and the argument is this: when a body moves on a surface, like this one, this is a piece of lead which I have attached to this, and let's suppose this is the moon. Okay. So the moon goes around the Earth, but what makes it go around the Earth? There must be a force. If there's no force, I'm pulling at this. And because I'm pulling, this thing goes around the circle. If I don't pull, then it flies off. There's a force. So the moon, if here's the Earth, and the moon travels in a line, and if there would not be a force, the moon would just drift along and go on in a straight line. But the moon is not going on a straight line. The moon goes down a little bit, and you can calculate how much the moon changes its direction, how much this little distance is in 1 second. And in 1 second, it's a 20th of an inch. So the orbit of the moon is in 1 second, 1/20th of an inch bent downwards. And that, in conjunction with his knowledge of the distance between the moon and the Earth, gave him everything he needed to calculate and to show that it's true that the force which lets the apple fall on the Earth is the same force than the force which keeps the moon up there. The moon is 60 Earth diameters away, so if that law is correct, then the force is diminished by 60 squared, and which is true. We know how far a body falls on the Earth, and by knowing that the moon falls 1/20th of an inch, it's the same law. So he had the law which is called the law of universal gravitation. I want to come back to my question, which I asked at the beginning. So, what Newton, he has one drawing in this book, which I will reproduce here. it's falling. Since I have only 4 more minutes now, make my let's say you are in an elevator. And you have an object in your hand. And when this rope is cut, the elevator falls with you, with everything in the elevator. And that's a free fall. So if you then let go of this object, the object will not fall down. Because it falls in the same way you are falling. In your free-falling elevator, the object will not fall down. And that's why the astronauts are weightless, because they are falling on the earth. They do the space shuttle, and it is directing the earth, is constantly falling on the earth, and therefore they are weightless. They are dropping, and everything with them is dropping, so they don't feel the force of gravity. I can't discuss Albert Einstein, but that's very complicated anyway. Einstein has some ideas about gravity. He showed that we don't need gravity to explain that things are falling. He said, take a lamp in space and another lamp sitting on the earth, the roof. And the person in the room cannot look out, so you don't know where you are. You don't know if you are in this lamp which is sitting on the earth or in the lamp which is in space. No masses around you. Now there's a person pulling this lamp up with a constant acceleration. If this person drops something and this lamp is accelerated up, this object will seem to fall down because everything else is accelerated. So if you let this go, it will fall down. This person does the same thing, falls down. These two persons don't know which one it is. They have no clue. They have no way of finding out if they are in the lamp which is standing on the earth or if they are in the lamp which is pulled up by an angel in space and is constantly accelerating. So he said there must be an equivalence between gravitation and acceleration. So we can explain gravitation also another way. And then he got into real strange mathematics. He used the curvature of space, and he said, think that space is a four-dimensional thing, with time being the fourth dimension. And try to think of this in 3 dimensions, because we can't think in 4 dimensions. Think of a billiard table or a piece of cloth or rubber, which is flat, and then if you roll a ball, it will roll on a straight line. But if you put a heavy object in the middle, it bulges, then this object seems to be attractive, but it only seems to be attractive. It's not a force, it's a curvature of space. So his idea of gravity is that there is no force between two masses. It's the space which is curved. And an object follows a certain line in the curve in space. And when space is curved more in the vicinity of heavy objects, then it must